Hi guys, welcome to Learn Electronics Repair. This video is sponsored by PCBWay and I have some of their PCBs here. This is one of the shared projects we find on PCBWay. So these are projects that people have designed, uploaded to PCBWay, and as a thank you to the author or the creator, if you or I order any PCBs from this design, which is just a one click to do, then the author will get a 10% commission from that sale. So these PCBs are from this guy, Imsai, yeah, if that's how we pronounce it. And these are dual op-amp test boards. But also, to be quite honest, these are also great teaching aids. So let me just show you these on PCBWay's website. Here we are at PCBWay.com, and I hope you can see straight away that PCBWay have quite a lot of services. So they manufacture PCBs. They also have PCB assembly. They will build your entire project for you. They have, what you can see here, many different options: flexible PCBs, rigid flex, aluminium, all sorts of things like vias in pads and plated half through and plated holes. PCBWay also have a special offer at the moment. You can see here, this is the Christmas big sale. So if you've not tried their service before, or you're just going to go back and try it again, I know a lot of you guys do that, then they have some special offers at the moment. So you can see we have discount vouchers depending on the value of your order. So orders of $30 or more, $5 off, $59 or more, $10 off, and so on. So they have some great offers at the moment. Typically, a set of 5 PCBs like the ones I have here will cost you $5 plus around the same in shipping, depending on where you live. To Spain, it's about $4.50, something like that. So for around $10, you can get 5 PCBs. But even better than that, if you use the discount code in the description to this video and you are setting up a new account, then you get $5 off your first order regardless of the amount. So you can get 5 PCBs effectively for just the cost of the postage on your first order. The PCBs we're looking at today are these ones, op-amp test boards. So this is a shared project. We can click on this, we can see the layout of the PCB, description. This links to a YouTube video on the author's channel and some suggested values for components you put in. If you want to try the board as a test board, we can just take a quick look. So you can see here the boards. This guy is showing you how to use them. So I will link this video in the description to this video again. Credit where credit is due. And if you want to see what the original author has to say about these boards, then you can watch this video. It is in English. So what we are going to do in this video is to have a look at op-amps. What are op-amps? How do they work? Specifically from the point of view of a repair technician. There's lots of ways to learn about op-amps. If you design your own circuits, there's quite a bit of mathematics involved in doing that. And there are a lot of considerations, different configurations. But from the point of view of repair, what we probably want to know is what configuration our op-amp is in on a device we're trying to repair, and what voltages to expect on the output given the voltages we have on the inputs. That's probably what we want to know, because we're going to try to determine, is the op-amp faulty or not, or is it giving the expected output for the inputs that we have. The inputs may be incorrect, but if the output is correct for those inputs, chances are the op-amp is fine. So I've actually populated a couple of these boards. I'll show you. Here is one I have populated using the suggested values from the author's video and from the PCBWay website. This is really set up so that we can test 2 op-amps one against another. This is great, for example, if you think you may have a defective op-amp and you have another one of the same, or if you think you may have some fake op-amp and you want to compare it with a genuine one. So we can perform quite a lot of tests on here, which we'll have a look at a little bit later in the video. I've just noticed I've missed off a couple of the capacitors, these decoupling capacitors here. These are just on the supply voltage rail, so I will solder them on before we use this. The other components I don't need to fit at the moment. These are if we want to put a load on the output of the op amp, but I'm not particularly interested in doing that right now. And these links here, these are just wire links. So you can actually feed an AC signal in here through a capacitor, which removes any DC component. But an op amp itself is a DC and an AC amplifier. So if we want to play around with this and learn, we're going to use an oscilloscope to see some waveforms on here. I think in our case, we actually want to see the DC levels, okay? The board's designed to use a plus and minus volt supply, but you can modify it to use a single voltage rail, such as 9 volts and ground. Here's a second one I've kind of populated. I know it looks a little bit messy, but this basically allows me to plug components in, so we can fit different value resistors. We can put a link in, we can put a capacitor in. There's probably a better way of doing this. I just cut up some parts of IC socket basically to get the little connectors I need, and this seems to work well. So I can, for example, take a resistor of any value I like to try, and I can actually connect it here, just plug in and plug in. Yeah, obviously you can do this on breadboard, but to be quite honest, this is like looking at a schematic at the same time as building the circuit. So the op amp actually fits here, but this shows you a schematic of the circuit you're building. And I honestly believe that if you are learning about op amps, these are ideal because it's much easier to visualize what you're doing like this than it is when you're putting the thing together on a piece of breadboard. Because on the breadboard you may think, well, which resistor is this, which one was that one? You might forget what you placed where. So I think these are great little educational aids. On this one you can see I've just built this half of the circuit using one op amp. I haven't populated most of this because I don't want to use it at the moment. Obviously I could do. So we can play around as well with different values on this, and we can do some practical experiments. Yeah, I mean, that's the way to learn this stuff. So what is an op amp? Well, op amp is actually a shortened form of operational amplifier. And operational doesn't mean it works. This name comes from the use of these type of circuits in analog computers. So before we had digital computers, we had analog computers that were effectively doing mathematics in an analog fashion. In other words, like, 1 volt times 10 volts is 10 volts. So actually the voltage represents the value. And although we don't use that type of circuitry anymore, the name stayed. But what an op amp is really is a differential amplifier. So this is the symbol for an op amp. It has 2 inputs and 1 output. So this is the output. And the inputs are marked with a plus and minus sign. This doesn't mean the positive input and the negative input. What it actually means is the non-inverting input and the inverting input. Okay. You can think of it, if you like, as negative as a minus, maybe get inverting from negative, but that's what they are. What it really means is that a positive voltage on here will give a positive voltage on the output, and the negative voltage on here will give a positive voltage on the output. So any signal you put into the non-inverting input will come out in the same polarity on the output. Anything you put into the inverting input will come out upside down, basically. So why do we call this a differential amplifier? Well, that's because the output is an amplified version of the difference between the inputs. So if you see a difference between the inputs, for example, this was 2 volts and this was 2.01 volts, then the difference is 0.01 of a volt. This is 0.01 of a volt more positive than this. So the output will be positive because it's non-inverting, and the voltage will depend on the amplification of the op amp. And the same the other way. If this was 2 volts and this is 2.01 volts, then the output will be negative 0.01 volts times the gain. What's the gain of this op amp? Well, an ideal op amp, the gain is infinite. Infinity. Infinity does not exist, we could say. It doesn't really exist in op amps anyway. But the gain is extremely high. 100,000 times 200,000, a million, 2 million, something like that. So what this means is that a very small difference in the voltage between the two inputs will cause a big difference on the output. Okay? If the gain of our op amp is 200,000, okay, and we put on here, for example, 1.0 volts, and on here we put 1.01 of a volt, okay, what will the output be? Well, it'll be positive because this is the higher, and it'll be 0.01, that's the difference, times 200,000. Okay, do a little bit with the maths and the decimal point, and I think we'll find the output on here would be 2,000 volts. Or it would try, but it can't. Why? Well, the voltage doesn't come out of like thin air. The gain, the increase in voltage, comes from somewhere, and where it comes from is the other two connections on this op amp, which I didn't draw because it has power supplies. It has a positive supply and it has a negative supply. And the output voltage is limited by the supply voltage. So the output can't go higher than the positive supply or lower than the negative supply. So what happens in this case, when we have 1.01 volts here and 1 volt here, the output will go up as far as it can. Where can it go to? The positive supply rail. So if there was plus 15 volts on here and there was minus 15 volts on here, the output would go to 15 or near. Most op amps can't actually go all the way to the supply voltage. They probably can go within a volt. Some op amps are designed to get much closer than that, but the voltage will go up as far as it can. When it reaches the limit, that is called saturation. So the amplifier output can no longer go any higher. So if you increase this voltage more here, that can't increase anymore. Okay? And that's called saturation. So that's what an op amp is. Now, I think you can see from this that an op amp is not much use as an amplifier because the slightest difference in voltage here will cause it to saturate. Yeah? So in this configuration, we cannot use an op amp as an amplifier. But what we can do is used as a comparator. So what a comparator will do is compare the two input voltages. Okay, plus minus. Let's put some voltage on our op amp. So if we want a comparator, we want something that we want to compare with something, yeah? You can only compare two or more things. You can't compare one thing on its own. Yeah, makes sense. So as a comparator, we have to put a voltage on this input, converting input. This is the reference. This is the voltage we want to compare with. Let's give a good example, just figures out in my head. We'll use a couple of 10k resistors. This is a voltage divider. We could have this connected to ground, and we could have this connected to plus 5 volts, for example. And if you watch the video I made on voltage dividers, you'll know because the resistors are the same value as each other, the voltage on here will be 2.5 volts, halfway. And we can now compare that with something else. Okay, so let's do something practical. Let's put another resistor in here. I won't specify the value because we'd have to figure it out depending on this component. And this component we're going to put a LDR, light dependent resistor. So this is a resistor that decreases in resistance as you shine a light on it. Okay? You shine light on, the resistance goes down. You put it into the darkness, the resistance goes up. Now, if we know the ambient amount of light in an unlit room, yeah, I mean, there's sunlight coming in through the curtains, but it's not lit, okay? We can put a suitable value resistor or variable resistor here so that the input here is lower than this one, okay? What will the output be? Well, if this is lower than this one, even by a tiny amount, the output will be the minus voltage rail. But you'll use 15 again. So we'll have minus 15 on the output of our op amp. Now, if somebody turned the light on, this photosensitive resistor would go down in resistance. So the voltage at this point would go up above the 2.5. And then the output of here would go from minus to plus. Okay, so this is a very practical example of why you would use this sort of circuit. There's many other reasons, and this is called a comparator. And that is the most basic use of an op amp. But I did mention that we would look at the operational amplifier from the point of view of repair. And we will find this type of circuit, and now we know how it works. We know, even with our multimeter, to measure the voltage on the two inputs, or measure the difference between them, plus or minus, and that will tell us what the output should be doing. If the output's not doing that, well, we could have a faulty operational amplifier, or for example, we could have a supply voltage missing, or we could have some sort of short circuit and whatever this is connected to that prevents it from changing the voltage. But we would know there was a problem there, yeah? And an important thing I'll mention now. So we discussed the fact that the amplifier doesn't create voltage. The voltage comes from the supply rails. That actually brings us to an important point about operational amplifiers, and very much so in this circuit. So, point one, the inputs on the operational amplifier are very high impedance. And in an ideal op amp, they are of an infinite impedance. That means that for all intents and purposes, no current flows into or out of the inputs on an op amp. They're voltage sensitive, but they don't draw any current. So the main reason is that important? Well, because no current flows in or out of here, the voltage on here is directly a result of the proportion of these two resistors. The op amp does not internally form another resistor like so in parallel with this one. So the op amp does not affect the voltage that is applied to the inputs. The same with this circuit. So one, input, high impedance. That's an important thing. And as we go through a few more examples, we'll look at the other most important things. So the next common use of an op amp. What happens if we take our op amp and we put a voltage on the non-inverting input, 1 volt, okay? And we connect the output directly to the inverting input like that. What will happen? What voltage will be on the output? Well, the voltage on the output will depend on the difference between the voltage on the inputs. We know that, okay? So if we put 1 volt on here, the output will try to go up to the supply rail. And the supply rail is, on the example, we had plus 15, minus 15. But when that goes up towards supply rail, it puts a voltage on the inverting input. The voltage here goes up as well. And if the voltage here went above that, this would tend to go down towards the minus 15 or straight down to minus 15. But that would put this input lower than this one. So it would have to go up. So you might think it'll oscillate, but it won't oscillate. What will happen is that when the voltage on the inverting input matches the voltage on the non-inverting input, so in other words 1 volt on here, it will balance, okay? And the output, well, it's connected directly to there, so it must be 1 volt. So you can see that if we connect like this, we get an output that is the same as the input. And if the input increases to say 2 volts, the output will go up to 2 volts. So this input will go up to 2 volts and it will balance again. So that's what the circuit will do. Now this is called negative feedback. Okay. We're taking the output and we're feeding it back to the inverting input. Okay. So what we've actually created here is an amplifier with a gain of 1. Yeah. Whatever goes in comes out. It's the same voltage. So what's the use of this circuit? Has it got any use other than just an interesting explanation of op amps? Well, it has got a use, and it's called a buffer. And the reason it's got a use is because we know the input of the op amp has no current flowing into it. It's a high impedance. No current flows in. Therefore, if this is connected to something like a microcontroller or something like that, it's not drawing any current from the microcontroller. It's just effectively monitoring the voltage on here, yeah? But the output of the op amp has a very low impedance. Ideally, the input impedance is infinite and the output impedance is 0. Of course, nothing is ever ideal, but it'll be close to that. So it has a very low output resistance, which means that this can now drive some load, okay, connected to here, without drawing any power from the device that's controlling the input. And that's a buffer. So this tells us 2 more important things. Number 2, the output of the op amp is low impedance. Z, the symbol for impedance, by the way. It's not Russian, okay? And the second important thing, which of course is the third one, is that the op amp will always try to balance the voltage on the 2 inputs if it can. When can't it? Well, when this voltage here saturates, it can't go any more and it still hasn't balanced the input yet, okay? And we'll talk about that in a moment. But number 3 is that the op amp will always try to balance the input voltages. Proviso, when it has a feedback circuit, because the op amp itself can't alter its own input voltage, but it can alter its output voltage, and it can use the output voltage or a proportion of the output voltage, this is important, to control the input voltage, okay? So Those three things really are the only really important things that you need to know about op amps, especially when you're trying to repair stuff. Because when you're trying to fix this, you're not trying to design the circuit to operate in a certain way. You're trying to test the circuit to see if it works as expected. And what's expected? Well, it's just the relationship between the two inputs to give a certain output. So you don't really need to know everything that's connected around this to know if that op amp is working or isn't working as it should. I just mentioned that with the feedback, the circuit feeds back the output voltage or a proportion of it to the input. So let's have a look at that. We'll just change the circuit a little bit, not much at all. We have our op amp again, out. We have our non-inverting and inverting inputs. Okay, we have some signal coming in here, and we take the output, and instead of connecting it directly to the input, we'll connect it to a resistor. Okay, and that resistor will connect to the input, and it will connect to another resistor to ground. Again, like we saw in this comparator, a voltage divider. This is also a voltage divider. It just looks a little bit different, but it's a voltage divider. But this voltage divider is connected between the supply voltage and ground. This one is connected between the output of the op amp and ground. Okay, so what it means is that a proportion of the output voltage will appear on the inverted input. If the resistors are the same value, say 10k and 10k, we should know, because the voltage divider, that the voltage here will be half of the output voltage, V out over 2, half of it, yeah. That also means that for a given voltage here, so this is 1 volt, to get 1 volt on here, this has to be 2 volt. So this is called a non-inverting, spell it right, amplifier. And the gain of the amplifier is solely determined by the ratio of these two resistors. There's a very easy formula for this. We'll call this one here VFB, voltage feedback. Okay. And what's the formula? Well, a good point to actually change the name of this to R feedback rather than V feedback. Okay. And this we can just call it R1 if you like. So the formula to work out the gain of this amplifier, it equals resistor feedback, okay, divided by R1 plus 1. Why is it plus 1? Well, look back at this circuit. So in this circuit, the output was connected directly to the input. So the feedback resistor was 0. Okay. There wasn't a resistor to ground, so that was infinite, R1, so 0 divided by infinite is 0, basically. Semantics of mathematics, if you like, but it's 0. So we can see the actual gain of this amplifier, we already know, is 1 volt in to 1 volt out, so the gain is 1. So when we start putting resistors in to change the gain with the feedback, we have to add the 1. The amplifier itself directly connected like this has already got a gain of 1. So it's the ratio of these two resistors plus 1. Okay, what's that come to? Well, that one there is 10k divided by 10k. 10,000 divided by 10,000 is 1. Plus 1 equals 2. And that's why we got 2 volts on the output. And by changing the values of these resistors, we can set the gain of the amplifier. So again, if you're doing repair work and you can see this sort of setup, you know you have a non-inverting amplifier. You know that the output will be in phase with the input. So the higher the voltage here, the higher the voltage here until it saturates. The lower the voltage here, the lower the voltage on the output until it saturates. And by taking the value of these two resistors, simple formula, you can work out what the gain should be. So you can easily measure the voltage on here, measure the voltage on the output, and you should be able to tell whether you've got the correct amount of gain. Okay. There's another common configuration, and that's an inverting amplifier. So let's take a look at that one. And this is quite interesting. So again, we have our op amp, out, minus, plus. You've noticed actually, I guess, that I've drawn this the other way up, so I put the inverting input at the top. That's just to make the circuit easier to draw and understand, really easy to visualize. This is actually a fact. So with an operational amplifier on a schematic, you will see it in various directions, and like this, plus minus, minus plus, you'll see them pointing that way and even downwards and upwards. It just depends on how the layout of the schematic is and what makes it easier to visualize. So these can be various ways, by the way. So back to our inverting amplifier. Again, we have feedback, negative feedback here. Okay, and we have an input resistor on this. So the circuit's slightly different. The non-inverting input, well, that connects to ground. Okay, so let's have a look at what happens with this circuit. And we can apply the same rules we've learned. So, or FB, just the feedback, or in, we'll call this. Could call it anything, but or in, why not? Okay. So what happens here? Well, imagine we have a signal coming in, AC, or this could be a DC voltage. As the signal or voltage goes negative, the output will go positive because this is an inverting amplifier. And part of the output is being fed back to the input. Okay. What's the voltage here? Well, you might say the voltage here depends on the voltage of the signal. You know, whatever's coming in, and the ratio of these resistors, if you like. Well, that's actually not the case. What was rule number 3? An op amp will always try to balance the voltage on both inputs. So when the signal coming in goes negative, the signal coming out goes positive, it's inverted, and the op amp will feed back enough of that signal to get the voltage on here to match the voltage on here. What's the voltage on here? Well, it's 0 volts because this is ground. Okay. As the voltage on the input goes more positive, the output will go negative, and it will go negative until it can balance the voltage here with the non-inverting input, which is 0. So what actually happens is with this amplifier circuit, if we look at the signal here, we will see a signal going in, or a voltage level. Okay. If we look at the signal here, this will always be 0 volts. The signal's disappeared. Where is it? Well, the only reason this is 0 volts is because the output voltage is changing sufficiently to feed enough signal back here to balance it, as I said many times. So the output will have a signal. Now, it will be inverted. So if our input signal is like so, our output signal will be like so, amplified by a factor which depends on the value of these two resistors. The formula for working out the gain is slightly different to this one. It is R feedback divided by R in, and that's it. So in the same example, if this was 10k and this was 10k, then 10,000 divided by 10,000 would equal 1. So the gain would be 1. The higher we make this resistor, the higher the gain. So for example, if this was 20k, then the formula now is 20k over 10k, the gain is 2. So the higher this resistor compared to that one, the higher the gain. This can confuse people because if you're fault finding, you may go onto the input of this op amp and say, okay, well, this is 0, it's ground, yeah? And there's a signal here. So where's the signal? There must be something wrong with the op amp. No, if the op amp is in this configuration, which is an inverting amplifier, that's exactly what will happen. And on the output, we will see the amplified signal. So those are the main configurations which we find our op amp used in, either a comparator, a buffer, a non-inverting amplifier, or an inverting amplifier. There's a few things we can note. One is that the gain can be less than 1. Okay, so you can have a gain of 0.5, which you may say is not an amplifier, it's anything, it is a reducer, yeah, an attenuator, that's the word, attenuator, but yes, the gain can be less than 1. You'll also find operational amplifiers with capacitors in the feedback network. The capacitors are there to alter the gain versus frequency, so it will have different gains at different frequencies. The reason for that is because a capacitor passes AC, and depending on the frequency of the AC, it has more or less impedance. Impedance is like resistance, it's just the resistance at a given frequency. So you can see that by putting capacitors in these circuits, you can make operational amplifier circuits that, for example, boost the high frequencies and cut the low frequencies. Think of tone controls, for example, on audio circuits. So that's one thing you will find, but it doesn't change the overall description of what the amplifier circuit is doing. It's still one of these. It just has a amplification that varies depending on the frequency. You can also effectively daisy chain amplifier circuits, so you could have the first one, for example, with capacitors in, which would reduce the amount of bass. The next one would then reduce the amount of treble above a certain frequency, and coming out would just be the middle frequencies. Okay, so things like that. I won't go into these on this description because the tests we're going to make on our op amps are DC voltage. We may do something with AC signals, but we won't go into this business of different response to different frequencies. That's another topic. Yeah, just be aware that you will find that in these sort of circuits. We can also use op amps to, for example, oscillate. We can make oscillators with op amps that oscillate at a certain frequency. We can make circuits that will, for example, give a time delay between a pulse on the input and a pulse on the output. We can make circuits that will give a set width of output pulse for a given change, or when the voltage on the input changes, we get a single output pulse. There's many things we can do. I'll give you one example because this is something you're familiar with. This is a comparator circuit. We know it's a comparator. If we feed in on the non-inverting input a sawtooth wave, yeah, that's a waveform like this. And on the other input, we put a voltage, yeah, a DC voltage, and draw it like this. What will happen? Well, we know about a comparator, so you can see that when the sawtooth goes above the voltage on this input, the output will go high. Okay, so we can see if we just draw this, this is the input, this is the output, so the output will go high. And when the sawtooth goes below that voltage, the output will go low. And the same thing will happen when it goes above that voltage again, the output will go high. When it comes down, go low. I think you can see now what happens if we change this voltage. What if we put it up here? Well, look, we still get the same thing happening. So when the sawtooth goes above our voltage, which is now here, the output goes high, and it stays high till the sawtooth comes down. Yeah, and the same on the next one. Okay, do you see what we've got there? It's a pulse width modulator, yeah? If that voltage is your feedback circuit, monitoring the output of a power supply, as the output of the power supply goes up, the feedback voltage goes up, it's higher up this sawtooth wave, that's fixed, and we get a narrower pulse, less output. Yeah, that is a pulse width modulator. So I hope you can see that op amps can be used in many, many ways. Op amps can come in various packages. Usually they are in a 8-pin or 14-pin IC package. These are through-hole ones. We also get surface mount ones as well. These are a very common op amp, the UA741. This is a single op amp in one package. We can get similar packages with more than one op amp. So for example, these LM358, these are in an 8-pin package again. These have 2 op amps, independent op amps in the package, and we can have chips with 4 in, such as this one, common quad op amp. So this has 4 individual op amps in one package. The power plus and minus are common to all 4 op amps, but the op amps themselves, inputs and outputs, are independent. So you can use 1, 2, 3 or 4 of the op amps in here in your circuits. Really, this is just to make the circuit smaller by using one package, for example, with 4 op amps. We even have devices like this one, AS15. This is commonly used to drive LCD displays, TFT displays for monitors and TVs. This effectively sets the color balance for each pixel on the screen, and this can change. You may guess from the name or the part number, AS15. It has 15 op amps in here. In fact, we can see the pin out for the AS15 here. So you can see in there effectively are 15 op amps. They're shown like buffers because they're used as buffers, but they are actually each one an op amp. In fact, it tells us here, rail-to-rail op amps. Rail-to-rail means they can drive the voltage all the way to the minus supply or ground, or all the way to the plus supply. You will sometimes find op amps in this sort of package. A metal kind of looks like a top hat basically, or rather a bowler hat with lots of legs on. These were used a lot in vintage equipment, but you can still buy these sort of op amps. Advantages of these in particular are that they are screened, so they're less likely to pick up interference. So you may find op amps that look like that also. Another thing I'll mention with the op amp, you see that on all the examples we've used here, we have a plus and a minus supply. You'll also find op amps that are used with a single supply voltage. Obviously, not having a negative supply voltage, they can only handle positive going signals. So in things like audio amplifiers, you will find the plus and minus. The same applies for instrumentation amplifiers. One reason for that is because the output of the op amp can't go all the way to 0 normally, whereas if you use a plus and a minus supply, as we put 15 and 15, the op amp can go to exactly 0. It's halfway in between. Okay, but you will find op amps in circuits use a single voltage supply. One of the common ways that is done is to actually put a voltage on the inverting input, similar to how we've seen before, with a voltage divider, and set the voltage here to be half of the supply voltage, and we can now effectively amplify AC signals here, and the signal will go between 0 or close to 0 and close to the supply voltage. But it's still basically alternating. It just doesn't alternate below 0. there are op amps that are specifically designed to use in these type of circuits. So you'll often see in data sheets an op amp that says it is for single rail circuits. Some op amps have extra pins on for things like offset and trimming, as they're called, kind of like calibrating the op amp so that 0 level is 0 level. And you may find other specialist op amps that have other signals as well, but they'll still all have this basic principle. They are an op amp. And you can get power op amps. So normally an op amp can handle maybe into the hundreds of milliamps. If you find things like audio amplifier chips, stereo amplifier chips, mono amplifier chips, motor drivers and these sort of things, they often are op amps. They're just a type that can handle more power and drive more output. But still the principle of operation is the same. There are other factors as well that effectively determine the type of op amps that you can use in given circuits. One of them is the frequency response. So some op amps you can put signals into the kilohertz or hundreds of kilohertz, some of them into the megahertz or even gigahertz. So some op amps will have a much wider bandwidth than others. Some op amps have a higher stability. So these are often used for instrumentation where you actually want to make accurate measurements of, for example, very low voltages and currents. You need to amplify the voltage or current to measure it, and therefore the gain of the op amp is critical to give you a calibrated instrument that gives you a correct reading. So some amps are specifically for instrumentation. And there's another factor, this is really related to the frequency response, and this is slew rate. So as I mentioned with, for example, our comparator, when the input on the non-inverting input goes higher than the inverting, the output will go from the minus rail to the plus rail. And I've shown that as a vertical transition. But that's actually not always the case. Depending on the op amp, it will always take a finite amount of time to get from there to there. And how long it takes is called the slew rate. So an op amp with a slow slew rate will effectively give you a transition more like that. And the higher the slew rate, the more like a square wave this becomes. Because we've been talking about repair, this is a repair channel, you can have problems in circuits where the slew rate is too slow, possibly due to some components around an op amp or the op amp itself, but commonly because you've got a fake op amp. So high slew rate op amps are more expensive than low or slow slew rate, and it is quite likely if you're buying from China for specific types of sought after fast slew rate op amps, you may be sold a remarked or rebadged one, a low slew rate, okay? So that is another thing that we should always consider when we're talking about repairing op amp based circuits. And here are our nice test boards from PCBWay.com. You can see we have on here 2 non-inverting and 2 inverting amplifiers. But we can actually use this board to test the other configurations as well. If we leave this resistor here open circuit, so we don't fit this resistor, and we don't fit this one either, so we've just got the inputs to the op amp, we can actually use this to make a buffer, yeah, 1-to-1 gain buffer. And if we connect from here, the resistor to ground, leave this one out, and we connect from here another resistor to the supply rail, yeah, we can actually make a comparator using this. So we can modify this to make comparator circuits or buffer circuits quite easily. So these are the things we're going to experiment with. We can also experiment by putting capacitors in the feedback network as well. We'll do this in part 2. Hey, part 1 is far too long already, some will say, but I think there's a lot to cover here. So I'll make part 2 sometime next week, I want to give a few days for you guys to watch this video and comment, because this is such a big topic. There are bound to be things that I didn't mention that I should have mentioned. Bear in mind, this is primarily a repair channel, and this video is all you need to know about op amps to fix stuff. So I don't feel myself as any need to go into any complex mathematics or design principles with this, but you guys let me know what you think. If you especially come up with some points regarding the repair side of op amp circuits, something I've missed, I'll almost certainly put that into part 2. The other thing in part 2, this is going to be pretty much all practical. We've done the theory now, so we can refer back to the theory we've done, but this is going to be the practical. We're going to build each type of these circuits, and we're going to test everything that we've described to prove if that's the case. We can also compare some op amps of the same type, see if we can find any fake ones, and we can compare some op amps of different types to see if we can prove that one has a faster slew rate than the other. These boards really are designed for dual rail operations. That's what I'm going to do on the next video. I'm not going to do any single rail stuff. Okay, I hope you really did enjoy that one, guys. I've enjoyed making this. I've promised to do it for quite some time. So comments below, let me know what you think, and I will definitely see you all soon with part 2 of this one. Thanks for watching Learning Electronics Repair. Ciao for now, guys.